Hello. Okay, so can you hear me at home?
Yeah.
Okay, I will. So today's lecture, we will say what is the class NP, what are reductions, what is NP completeness, and then we start with proving reductions from tree sets. Okay, so first I apologize for the homework. It's first time I need 5 warnings before I have a correct version, but it's good for you because everyone who submits homework gets the point. Okay, and now I'm scared that I'm crazy. I cannot think anymore. But okay, hopefully it passes.
They change the homework every year.
Yeah, some homeworks get changed every year, but usually they get changed at most once. Not, yeah. So, but so it's important. So I have this. I cannot memorize anything. So I like if I teach before I start the proof, I need to reinvent it. So and uh, teaching the same course many times doesn't help me much. So that's why I like mathematics because everything is logical and then so in my family it's a problem that nobody can remember anything. And so yeah, but it means that sometimes I'm really tired and then it happens. Okay, let's not waste time about it. Today we have very easy lecture, fortunately. So let's start with it. So yes, the definition of class NP. What is P versus NP problem about? So think about solving crossword puzzle. So like solving it from scratch, you need to do hard thinking work and searching and so on. But if somebody else fills it in, you can check easily that it's correctly filled in. And so class NP corresponds to problems for which there is a really easy method to check a correct solution, but finding solution might be difficult. So when we speak about production problems, then we say finding solution is difficult. When we go from production to decision problems, the definition is a little bit different. So when we give an input for which the answer is yes, then it's possible to provide a proof for which it's yes. A proof of this thing. For example, if you're given a Hamiltonian, if you're given a graph, and the question is there a Hamiltonian cycle? Then if the answer is yes, somebody can convince you that the answer is yes by showing you a Hamiltonian cycle. So that's the idea. So think about you're a judge, and there is a way to convince the judge that graph is guilty of having Hamiltonian cycle. Okay, so let's go to formal definition of those languages inside the class NP. And so for this, we need a definition of verifier. Or let us say that a machine verifies a language. The definition. So a machine M is a verifier for language L. Or language. So if it receives two strings, first one is the input of the language, second string is called certificate, and then it decides accept or reject. The idea is that if the input is in the language, then there should exist at least one certificate. If it's not in the language, then no certificate should work. So if the graph is not guilty of Hamiltonian cycle, having a Hamiltonian cycle, then the verifier, the judge should reject all the proofs. And so it's forbidden. So a judge is, in practice, a judge is extremely careful not to convict somebody who is not guilty of anything. So M is a verifier for the language L. If L is equal to precisely those inputs for which there exists a certificate, so that the machine accepts the certificate. Okay.
So what is certificate?
So certificate is just a string of any length. So machine receives two strings, input. So a string over the alphabet of the language, and a certificate just a string over a different alphabet or the same alphabet, doesn't matter. And so we say that W is in the language if and only if, or let me write it a bit longer, a little bit less technical. So W is in the language if and only if there exists a certificate for which the machine accepts. So this is. So if W is not in the language, it means that every certificate is rejected. So that's the definition. So for example, in the Hamiltonian cycle problem, the verifier for this language can, for example, W will be a graph and C will be a list of nodes. And the verifier checks that every node of the graph appears exactly once in the list and that subsequent nodes are connected, as well as the last to the first node. And so it checks that all the nodes appear and all of them at most once. So basically 3 checks if you would program it like that. Okay. Let's okay, now the question is, what is a polytime verifier? So here the polynomial time concerns the first input of the machine, not the second one. So it might have if the only certificates are huge, then we don't call it. Okay, just the machine should run in time polynomial in the first argument. So we say that m time verifier if there exists polynomial such that MWC out in time P of length of W. Okay, so our verifier for Hamiltonian cycle problem runs in linear time or quadratic time if one take Turing or whatever. So in polynomial time. Okay, let us consider another problem, which we will use more today, which is integer programming. So the input will be a matrix and a vector, and we check whether it defines a system of inequalities that's satisfiable. So input is a matrix with integer coefficients n times m, and then a vector b and m, and the question, does there exist x in Zn such that ax at most? And so everything has to be integer. So there exist solvers, like in the practice, MILP solvers are used. It's a little bit more general. So you can have both. Doesn't matter. So this is integer programming, and here this problem is also in NP, but it's far from obvious why it is in NP. And the reason why is it far from obvious? The reason is we need an x with integer coefficient, but this x can be huge. So let us have another problem, Diophantine. And here the input is a polynomial with integer coefficients. And the question is, does it have a solution, integer solution? So polynomial with coefficients in Z, and the question.
Polynomial in one variable.
Yeah, in one variable. Yeah, sorry. Question, does there exist x in Z so that P of x is equal to 0? So, and we know that this problem is not an NP. So you might say, oh, the verifier just checks the polynomial. But there exist polynomials for which the only solutions are huge. And so it was proven by in 1970 by Matyashevich, it's Russian, and also 3 other people who worked a lot on this. And they proved that this is an undecidable problem. It's famous. It was Hilbert question. So he said, does there exist an algorithm that can solve any polynomial, find solution if one exists, or say there's no solution?
How is it possible for these to have large distance? The highest term in the polynomial will dominate the rest.
Yeah, so there are positive and negative variables. So there is actually some hobby mathematician. Well, first, can you find solution? Okay, this is in 3 variables. The world in 1 variable is more tricky. So,
Eating in cubes.
oh, sorry, it's not in 1 variable. I'm sorry, in many variables. Sorry. Okay. No, you're right, not in one variable. Thank you very much. Okay, I get scared, but again. So, okay, so here we have many variables and it has integer solution, this equation, right? You can see it, 3, 1, 1. And then
They didn't use.
sorry, I meant, oh my God. Yeah, I meant cube so far. And so there is a funny story. So here, the same question, but we replace 29 by 3, by 30. Okay. And so here, only solutions, they're X, Y, Z in the billions. So some hobby programmer. And now there is the other question, what about 33? And so it's open question. So so people don't know if this has solution or not. It's like in mathematics club, it's a question well known for hobby people. Okay. So, yes. Now I will give a second definition of the class NP. Oh, okay. So I forgot to say class NP problems that have polynomial time verified, but you guessed it, right? Or did I say it? Yeah, I tried to understand how how bad is the current state of my brain. Okay, so other definition uses non-deterministic Turing machine. It's Turing machine that has two transition tables. So now there's a little bit, how can you compute with two transition tables? And so there does not exist computation. There exists something like computation tree. Depending on which table you choose, you go to the next state. And remember, Turing machine, the table tells you, or the transition function tells you for which cell and for which symbol on the cell and for which state to do which write, read, and move. And so there are two possible next actions, next ripples. And so that means that for a deterministic Turing machine with just one transition table, computation goes in a line. For the non-deterministic machine, there are like two worlds, one where it follows one table and the other, and we get a binary tree that creates all the computations. And it represents heuristics that you might implement in an algorithm. So when you program, this translates to a Turing machine. And so this is a world where there exists secret knowledge to solve NP-complete problems, to solve difficult problems. This is represented by the machine. And this defines the class N time. Sorry. And I say, what does it mean for a machine to accept? And so in the leaf of a computation tree, there is either accept or reject. But now we have exponentially many leaves that either say accept or reject, and so on. So we say that the input is accepted if there exists at least one leaf in which the machine accepts. Input is rejected if all the leaves reject. So that's the definition. And now we can define the class N time. A language L is an N time of F if and only if there exists a non-deterministic Turing machine that recognizes or that decides the language. So this is also a short definition. This definition is the reason why we use the name NP, non-deterministic polynomial time. Oh, sorry, yeah. So there is our theorem that says that NP is equal to the class C of N times N to the power C. Okay, so now what I'm saying is coherent, I hope. No, I wrote, okay, you can choose. I choose this one as definition because it's just with deterministic polynomial time machine. Usually students suffer a bit more with this, so I use the difficult theorem for as the difficult one as definition. And CIPSR, indeed, I think this is, I forgot what is chosen. Okay, but theorem says that they're equal. So you can use either one as definition. Okay, so let us do an example of a non-deterministic Turing machine to that recognizes Hamiltonian cycle problem. So how the machine operates. So machine goes to the first node of the graph, and then iterates over the neighbors of this node. And each time, so the first table will say, okay, I go to this node. The second table say, no, let's go to the next node. And so when the machine computes, arrives in a node, it uses the two tables to choose whether it goes to the next node, yes or no. And so eventually it will choose a node, and if it chooses another node, then it rejects. So in this way, it will take a random path. But every node that was chosen is written inside the memory because it needs to check that the next, when it goes to a new node, that it's a new node that it didn't visit already. If this happens, machine rejects. Yes? Good question. I forgot to tell. So time is the longest branch in the tree. And so the longest distance from leaf to root. Yes, very good question. Any leaf.
You are required to have.
Yeah, they have all the branches have to be short in order to have a short runtime. Okay, more questions? Yes. So let us look to one of our problems. Oh, I already deleted. So integer programming problem can also be solved by non-deterministic Turing machine. So how could we do it? So integer programming. So there, the question is, does there exist a vector such that a bunch of inequalities are satisfied? So the plan is to let the non-deterministic machine guess this vector. So it will go to some place in the memory and then use the two tables to write either zeros or ones. One table will write one will write zero, and then it goes for a certain amount of time to the right, and it guesses all the numbers. And then it makes a check, checks that all inequalities are satisfied. Okay. And so now we might have an idea how to prove the theorem. So both directions are rather easy. So imagine that a language is decided by a verifier. What could be the non-deterministic machine that runs in polynomial time and decides the language? Yes, exactly. Right? And so if we have a verifier, we have such a machine. And now the other direction. If we have such a machine, how could we create a verifier?
The rank that goes to the exception.
Exactly. Certificate is branch in tree. And so the verifier simulates the non-deterministic machine, but to know which transition function it will use, it looks to the certificate, to the next bit in the certificate. We know that this one runs in polynomial time, so the length of the certificate is polynomial, and this machine, yeah, just checks polynomial many steps.
Actually need
like, why do they know the time of the the maximum, like the maximum? Yeah, the maximum length of a branch. Why not? Why not? The minimal length to an accepting node. Well, if it rejects, it's already a problem. But also it doesn't matter because you can always clock the machine. So we are using multi-tape machines. By the way, so I wrote some notes, and then Sipser book is kind of annoying because in chapter 9, without warning, well, I didn't read the third edition of the book. I read the second one. But as I quickly scanned the first chapters, there is no clear message. We will use multi-tape machines, but then in 9th chapter, it's only about one tape machine, and it's kind of sad to do it like this because it's non-standard. But okay, there is good reason to do it like this because simulation theorem with many efficient simulation with many tapes is kind of tricky.
And is a non-deterministic Turing machine that takes X space.
Okay, that's a good remark. And so we've proven their equivalent. Let us prove some inclusions. So let us go. Let us prove these inequalities. So the first one is P is an NP. So why? Imagine we use certificate definition. Well, we can just ignore the certificate and run the polynomial decision procedure. Here in this definition, we just take two equal transition functions. Then all leave accept or all leave reject. So now let's prove that NP is an X. Oh, actually, we can do better. Yeah, P space. So why is it true? Because branch at most polynomial space. Yeah, so you choose that you use this definition. What he says is, let's go depth first way and search whether we find accepting leave. Another way to say is, let's look to certificate definition. Here, the length of certificate is not bounded, but the machine runs in polynomial time. So we can assume length of certificate is at most a runtime of the machine, because machine never has time to look further inside the certificate. And then we can brute force all certificates. Since certificate has polynomial size, brute forcing over it requires polynomial time. And so we just keep a counter, increase it, and then run the polynomial time decider, polynomial inside the first argument. So
but if we count all the vertices, will be two in parallel.
Yeah, you're right. It's exponential.
But so why this P space?
Yeah, so P space means that you can solve it using polynomial amount of memory. And here we don't care about the time.
Okay.
Yeah. But last lecture, we proved that P space is inside X. Because, yeah, there are most exponential configurations, and if one is repeated, the machine doesn't help at all. Okay. So that's good. What else should I? Okay, so in the exercises, there are some exercises. So if A is an NP, B is an NP, A union B also an NP. Same for intersection and so on. So there are a bunch of properties. So there is cleanly star where you concatenate any number, like in the homework. There was also like a refined. Okay. So this also preserves properties of NP. That's for the language. Okay, and now you know what is this famous class NP, and you will see that all problems for companies, they are inside the class, and almost all problems are inside the class NP, the corresponding decision problems, or they are, or either they are complements of problems in the class NP. Okay. So now let us define what is NP completeness. But for this, I need to say what is reduction. Reduction is a way to say that one problem is easier than another. So if we can reduce one problem to a problem for which we already know the solution, then we are done. With that we can solve in polynomial time, we are done. Okay, and so let us write the definition. So it just a reduction is transformation of one problem to another problem. So we say that A poly time reduces to B. Sorry. We say that F is a polynomial time reduction if we have a function from sigma star to gamma star. This poly time reduction so polynomial reduction of K to B notation. Okay. So if you can evaluate F in polynomial time in the input length as usual, and if answers yes or no do not change after applying reduction. So two properties. So F of W is evaluated by poly length of W. Second, W in A, if and only if F of W in B. So to make it in the picture. So we have input alphabet of first problem, input alphabet of second problem. Then we have a set A, a set B, and F puts problems inside A to B, problems outside A also to B. So definition of reduction. So let's do, okay. I should start with an example because definition is boring. So let us think about independent set problem. Yeah. So here input is a graph and an integer. The question is, are there at least k nodes that are pairwise disconnected? And this problem, polynomial time reduces to the clique problem. So you can think clique problem, set of nodes pairwise connected. So reduction goes by inverting the graph. So let me write the problem because then we can use it a few more times in this lecture. So the input, the graph, and k, and the question exists k nodes pairwise disconnect. So, okay, it's too easy for you, I think. Okay, so is there an independent set of size 3? Yes? Yeah, I also don't see one, but for 2, it's okay. We can take this one and this one. Yeah, because with a cycle of length 5, you cannot have 2 nodes are always neighboring. Okay, and so example. And poly time reduces. Okay, being polynomial time reduces, so A polynomial time reduces to B, A is polynomial time reduced. So if such a function exists, we write A is less than B, meaning that's kind of easier. So almost all, in the first 8 lectures or something, all the problems, you can place them on a line. They are comparable. So the line starts with problems in P. and then we can place here. We can have so the problems in so there exists a kind of NP complete problems. They're the hardest one. Oh, okay, that's too early to put a line. Oh, let's first make some abstract properties of reduction. So if A polytime reduces to B and B polytime reduces to C, then A polytime reduces to C. So it seems logical, but it's a little bit thinking is needed why this is true. Yeah. So we can compose the functions, but note that inputs can expand in size. So there is I write here another set.
Здесь вам?
Нет.
Здесь нет мамы.
And,
Может, мама там?
and C.
Удобно.
Yeah, indeed. That's a property that we need. So if we have a reduction F here and another reduction G here, then we can consider the reduction H of W equal to G of F of W. Okay, so runtime of F might be, so the runtime of F might be n to the power C for some C. For G, we might have n to the power D. So then the runtime of H will
Так,
be
что?
input length
Лекция.
of G.
Почему опять неожиданно?
The input has expanded maybe
Как она у
to
тебя
n to the
неожиданно
power
выросла?
C, but not more.
По средам. Да, все же.
Machine making the
Ты
transformation of
какой
D
точно?
cannot
не
write
очень.
more than its
У
runtime.
меня работа.
Максим, работа не должна мешать учебе.
Not treat, no
Что,
longer
очно к нему нельзя прийти?
Можно.
Там же понятней.
plus one,
Нет, так тоже понятно.
plus
Тем
one.
более у него очень хорошие делает
So
потом
if G
notes лекции.
is a machine that runs input size to the power D, then the runtime of H is n to the power C times D, which is still polynomial since C and D are constant. Okay. So now second example. Nice. Second property. So if B is in P and A reduces to B, then A is in P. So property 2, if A reduces to B and B is in P. So then A is in B and P. So why is this true? So we want to know whether a certain input of A is in the language, yes or no. What do? We evaluate the reduction and run the decider of B. And then we have, for the runtime of the combined procedure, we have a similar trick. So we run the reduction, and then if the decider runs an input length to the power D, the combined decider is n to the power CD. Same is true for NP. Then A is also in NP. So why is this true? So there are two definitions of NP. You can choose either one.
The second one is
With non-deterministic machines, because you don't need to change anything. It's the same algorithm. And since the second machine is non-deterministic, the first one is deterministic, but we can also view it as non-deterministic machine. So it runs, you run them consecutively. Okay. Yeah, that's enough properties. Now let's do a less trivial example of reduction. Let's go back to binary integer programming. Oh, by the way, you can also use this to prove the contrapositive. You can also use reductions to prove that a certain function is, for example, not in P. And so if A reduces to B and A is not in P, then we conclude that B is not in P. Okay. But I so let us go back to binary, integer programming. So if somebody, by the way, I don't know why it is an N. I already said I don't know why it is an NP. Integer programming is an NP because because it can be proven that solutions always exist. And so let us remind you what is the input. So input is A and Z n times M and B and Z n. M. And the question. Does there exist n which that AX and B? So, and this problem isn't NP, but I keep forgetting. Well, actually, I asked my friends why is it an NP, and they said, "Oh, if you remember, you need to remember linear algebra and Cramer's rule." But then there is underdetermined system, and so okay, I understand that sometimes. So Cramer rule. So they say that let's look to. So let's look, if I assume there exists a solution, then they say, okay, then let's look to the coefficients of this solution somehow, and then solve the system. So create B prime, and then solve the system AX equals to B prime, but then and if B prime has simple coefficients, then this Cramer rule is just calculation of determinant. It happens in polynomial time, so the size of determinants are polynomial in the bit size of the numbers. But then I don't know why you can assume that there exists a B prime of polynomial size. So it's circular. But okay, it would be strange if this problem, I mean, if there is an error, I believe that it's an NP, just I don't know the proof yet. So I need to carefully reread linear algebra and algebra book, and then I guess it will be obvious. So okay, so but if somebody knows it, please tell me.
I can tell that this problem is definitely equivalent to finding short vector in the vaccine, and that's. I believe this is a hard problem because it's.
To prove that short factor problem
yes,
is, yeah.
But at least I know that the short vector problem it's like some cryptography relies on it. So,
Yeah, there is no discussion. Yeah. It's such an important problem that I mean, 10,000 of people that are really clever have used it, and they would refuse to say it's an NP if they don't know the proof. So it would be really strange if this argument is false. But actually, so you have to be careful because traveling salesman problem is not known to be an NP. So there you when you give the inputs are coordinates of locations, rational coordinates. And the question is there a cycle that has at most a certain length and that visits every coordinate exactly once? Every point exactly once. And the problem is that taking square roots with arbitrary precision is a difficult problem. And you might need to take square roots with huge precision.
Taking square roots is easy. It's hard to know how much precision you will need.
Yes, that's what. Yeah, that's what I want to say. So you have an integer, and then you need to take a bunch of square roots and compare it to this integer. But the problem is that the value of these square roots can be really close to this integer. It can be a little bit above, a little bit below. And this margin can be really small. So you are forced, in order to confirm that the cycle has short length, that it takes long time. And so it's kind of painful, like on the radio, people say, oh, famous NP-complete problem, traveling salesman problem, you're given the coordinates, and then they say, okay, but that's one where we don't know if it's an NP. So, okay, but let's not be distracted and do a non-trivial reduction. So let's reduce the independent set problem, which is there, to integer programming problem. Okay, so I will write the reduction in this direction because I've written the problems in this way. So what is reduction? Oh, you're given graph. Let's do it with example.
Yeah, there is a pretty short reduction of integer programming problem to minimum matrix power problem. There is no.
Yeah, last year.
Reduction of
Reduction of
vertex cover to integer programming, or integer programming to vertex cover.
Yeah, last year I used vertex cover, and now I use.
power to.
I will now use independent set. It's almost the same reduction because you will soon know that independent set and vertex cover are almost the same problem. Essentially, it's really easily reducible. Okay, so here is an input graph and integer. We need to map it to a matrix and set of vectors here. Okay, and so I will label the variables. So the variables I will be using corresponds to nodes. They will. The idea is that the variable is 1, then this is in the independent set. If variable is 0, it's not in the independent set. Independent set exists if all inequalities are satisfied. I will write not a matrix and a vector, but just separate inequalities, and then you can transform it to this format, right? I will also use bigger than inequalities, but just by negating the coefficient, you have less than inequalities. So note that we are using Z here. Okay, so what will be the inequalities? So, well, first I will say that XA plus XB plus and so on, XE should be bigger than K. So the idea is that in the independent set, we should set at least K variables to 1. Oh, sorry. And then I first require that all variables are bounded by 0 and 1. And same for XB and so on. And so I will define, this is a common transformation when you want to solve independent set problem with constraint programming or for example, you will do exactly the same reduction. And now I will also require that not two nodes are selected. So no two nodes are selected that are connected. Yeah. So for every edge, for example, let's look at this edge here. And so I will say that XA plus XB is smaller than 1. And then I do the same. XA plus XE. And then for all the edges. XA plus XB is smaller than 1 for all edges. Okay. So now what are the values of N and M in this reduction? So number of variables is number of nodes. And number of inequalities, the M, will be equal to twice number of nodes plus 1 plus number of edges.
Quadratic.
Yeah. So quadratic in number of nodes. So the claim is that this reduction from the graph to the matrix AB can happen in polynomial time. Because we need polynomial equations, N and M, here the N and the M are polynomial. And A is is of size N times M, so writing all coefficients can be done in polynomial time. Okay. So we know it's in remember, reduction, two criteria. Function works in polynomial time. Second criteria, you remember. The second part of definition that we need to check is equivalence. If this is in the language, then this must be in the language and vice versa. So if tasks present reduction, those are two things you have to say. Okay, so equivalence, it's almost by construction. And so if there exists an independent set, then there exists a solution of all these inequalities. Then we just set corresponding variables to 1 and the others to 0. And then this is satisfied. If we have k1s, then this is satisfied and so on. And now vice versa. If we have solution here, then it must be an independent set. An independent set we read off from the variables. And we know the size is at least k, and this guarantees that no 2 points are connected. Okay, so this is a non-trivial reduction. Okay, so now let us finally say what is NP hard and NP complete. This we don't need anymore. So language L is NP hard if for every language in NP, we can reduce this language to L. So for every, or let's call it A is NP hard if for every B, and let's do it like this. For every A in NP, A reduces to B. So NP hard means harder than any language in NP. Extremely easy, yeah. So NP complete. Two conditions. One, B is in NP and B is NP in NP hard. Okay, so let us now. So questions? So all the languages we have discussed, all examples there, NP complete problems. Now, of course, I've got for D of Fantine, which is undecidable. How can we prove that a language is NP complete? The idea is that first we will prove that one language is NP complete, and then we will reduce this language to other language, to the particular language, for example, independent set. And so there is magical language that we will use, that everyone uses as first NP complete problem. And maybe you heard about it in other course. So it's called three-set problem. So this is our first problem. I will say soon what it is, but what is the property that we use? So little lemma. So if A is NP complete of NP hard, and B is and A reduces to B, then B is NP hard. So in picture, it's quite easy. And so let us have an axis of all our points here. So I told you that most problems that we will consider in the first lectures, first half of the course, they are comparable. Either one is easier than the other, or the one reduces to the other, or vice versa. And so the easiest problem, according to polynomial time reduction, the easiest class of problems are the polynomial time solvable problems. Then the second class, the second point we have here is NP-complete problems. And here is all of the class NP. Right? So when we prove that the problem is NP hard, we say that the problem is either here or more at the right. It's heuristic way. It's not exact way because not every pair of problems are reduced to each other. They're incomparable. But okay, for now, so the idea is that if we prove that A is in this point, and we prove that B is harder, so at the right of this point, then B is also NP hard. So that's our plan.
And after NP complete, going NP part of it.
Yeah. So we can define P space complete and X complete. By the way, last lecture we had a question, natural examples of X complete problems. And then I told there is a game with drawers, which is like simple to state, easy to state. But there exist problems called generalized chess and generalized Go with Chinese score rule. And they are X complete problems. So in chess also with the rule that no state of the game is repeated twice. So there is another rule for termination that says if nothing is captured, I rarely play chess, but if nothing is captured in the last 30 moves and no pawn is moving upwards, then the game finishes. But with this rule, I think it's P space complete. So it's kind of tricky. Yes. So that are all the points. But for practice, only these 2 points are relevant. Cryptographic problems are somehow here. So given a number, can you find a factor of this number that is small? So this is kind of problem related to certain public key cryptography. So it's believed to be somewhere between P and NP. But they are not production problems in industry. This is weird. Yeah, it's both in NP and co-NP. But okay, so the Pratt certificate is a little bit that's too difficult for this course.
Are you sure it's too difficult?
No, to show that it's an NP is easy because the small factor itself is a certificate. You can, if you know the small factor, you can verify it. But then the other way to prove that this problem is in co-NP, okay, but we don't know what's co-NP.
And you just present the real factorization and prove that each factor is actually part of it.
Yeah, but the question is, how do you prove that the number is prime?
Factor 5 P minus 1.
Yeah, you're right. So that's called the Pratt certificate. But then factoring for P minus 1, you use some result in number theory. And I don't remember it. Okay, but let's not speak about this now and continue with the lecture. Okay, so how much time is left? 20 minutes or something. Okay. So now there is an important problem. It says that 3 set is NP-competent. And I will show it not today, not next lecture, but the lecture after this. It's called Cook-Levin theorem. So, Levin. Set is NP-complete. And now I need to say what is 3 set. By the way, Levin was born here in Russia. But he once said something bad about the government, and so he has to
was hidden most of his life, and he had to scared for his life. So, and then finally he arrived in the US. So nobody knew where he lived, just somewhere, somehow papers appeared. Okay. Yes. Oh, I forgot what I want. I need to say what is three-set problem. Okay, so input of this problem is Boolean formula. What is Boolean formula? Boolean variable, you know, they're variables that take values 0 or 1. Boolean operations are and or negation. And so you can build a formula using these three operations. That's a Boolean formula. Okay, so for example, x or y, let's say x or not y, and not x or y. So here is Boolean formula, and it has easy interpretation. So it's true if and only if x equals y. Okay, and this is kind of special formula. So formula in CNF is a formula that consists of ends of ors. A clause is just an or of several literal. Let's start. Literal is a variable or its negation. X, not x, y, not y, v or x, and so on. Then a clause is called disjunction of literals, an or of literals. So here we have three clauses in the formula. So it is or of literals. And then formula phi is in C and F if it is an end of clauses. Then we say that phi is in K, C, and F if the length of the clauses is at most K. So the clauses have at most K literals. At most K. Oh, yeah, also Levin is Jewish. That's also why government was going after him. So he never received his PhD. Despite known by everyone, not only for this theorem, but for cryptography, average case hardness. And his supervisor was Kolmogorov. So Kolmogorov used all his influence so that he could at least do the defense of the PhD. But then to actually receive the PhD, even more influence, which it was not. Okay, let's this history long time ago, it's 1960 something. But then it's funny because Levin didn't want to publish this theorem. He said it was too easy, so it would be a humiliation to publish this easy thing. And so Kolmogorov went to him and said, no, it's very important. But he says, no, I tried to prove that P different from NP and I failed. And Kolmogorov said, no, this is not a problem. You need to publish this. And then they made a compromise. So there was another result called Levin's search. So if P is equal to NP, we actually know already what will be an algorithm that works. So the algorithm will try all Turing. So we give an input of a problem. It will try all Turing machines in parallel to generate certificate and then check the certificate. So that's the algorithm. So if P equals NP, we already know the algorithm that works in theory. But the idea is that the Kate machine receives 2 to the minus K fraction of the runtime. So if this machine is really complex, this algorithm has a huge linear coefficient to work. And so it's kind of nonsense algorithm. Okay, so then he said that Levin said, look, this is a school result to Kolmogorov. So I will put this result together with this result in the paper, and then I think it's not embarrassing to publish. And so nobody knows about, I mean, okay, many people know, but fraction of people that know about Levin search is way, way smaller than the Cook-Levin theorem. Okay, so okay, but this is stupid. I should define what is three-sat. So three-sat problem input is a formula in 3CNF. And the question is, can you find a signed variable? So the formula evaluates to what? CNF, and then the question, does there exist X? Formula phi in 3CNF, does there exist so that phi of X equals to 1? And so X is a list of Boolean variables. So here we have formula, is it satisfiable? Yes, yeah, we can take,
Well, all variables set 1.
yeah, because every clause has a positive variable.
All
All-
2 sockets.
Yeah, if we set all variables to 0, then it's false because the last clause is false. Okay, so three-sat is NP complete. In 2 lectures we prove it, and now for now we believe that this is true. It means for every problem in B we can build a reduction to three-sat. Okay, now we will prove that independent set problem is NP complete by reduction from three-sat. So here is the example. And okay, so in formula, yeah, clauses have length at most 3. There are variants where of the definition where they ask clauses to have exactly length 3. And some variants also require that all 3 literals are different or even come from different variables. So it's kind of tricky, but doesn't matter much because it's possible to transform them into each other. Well, if the variables come from 3 different literals, you need to be a bit careful to understand. Okay, I need to think about it. Maybe I will add it as a question to some homework, whether it's the same. Okay. I mean, whether it's also NP complete. So,
There will be a part which is 2-sat, which is polynomial, and there will be a part which is 3-sat.
yeah. It was in previous seminar, but in the end of the seminar, the task was to prove that 2-sat is polynomial time solvable. And so now I will prove that independent set is NP complete. So I will make a reduction from 3-sat to independent set. So that means we need a function mapping an input from this problem to this problem. So let's do it with an example. So here we have a formula from 3-sat. Every clause has length at most 3. Okay, and let's for convenience add some clause of length 3. Otherwise, let's at least have make it a bit nicer, the picture. Okay, and so the plan is that for every clause we need to create a graph now and a number k. So for every clause we will have 3 points. I mean, number of points will be equal to the number of literals, and we mark these points by the name of the literal. So we have x dot, y, z dot, and z x. And now we connect points that are labeled by opposite literals. So we connect y to not y, and z to not z. And we also connect
then z to
Yeah, and we connect also the nodes of each class.
Z.
Yeah, there are more. Okay, let's do all of them. Y goes. Yeah, okay, that works. Right, we just have two negative ones and yeah. Okay, and now we also
The left
need.
triangle has an X, the upper triangle has X negative. Should they be connected?
Yes, thank you. So, and the number here is number of clauses. So in our example, it will be 3. So that's the reduction from formula to graph. So we can do it and so we have to check two properties of the definition. First, we can evaluate function and polynomial type. And so this is easy to believe because the graph, the size of the graph, number of nodes is number of literals in the formula, which is proportional to the input. And then number of edges quadratic and the number of nodes, and then writing this number is really easy, just the number of clauses. Okay, second condition is equivalent. So if this is satisfiable, then independent set exists. So, well, in every clause we choose one literal that is true. For example, if we take all positive ones, then we can choose. So we noted before that we can choose all ones here. So to find, so given this assignment, we can find the independent set. So just pick a literal that's true, and in our case, we just pick positive one. And now I claim that this is an independent set. Because in an assignment, we never have two opposite literals. So they cannot be connected by an edge, and we choose in each clause, we chose one variable. So here we have reduction. Now the opposite, if there is an independent set, we have a satisfying assignment. So what we do is, so for example, should we set x to, so if we have a variable, should we choose 0 or 1 for the assignment? We just check whether this variable is selected or its negation is selected. And then we choose a value. If the variable is never selected, then we can set it to anything. And this works because the property of independence guarantees that no variable is selected both by its value and its negation. And we are guaranteed that the formula is true because every selected literal is equal to 1, and there is such a selected literal in each clause. Okay, I pause a little bit. So is it clear why this is equivalent? Okay, at home I cannot see the faces, so it's better if you show them, and then I can, if you're looking in a painful way, I can repeat everything. Okay, so we have proven that independent set is NP-complete, since we agreed to believe this for now. So now let's go to another reduction. Let's prove that vertex cover problem is NP-complete. So what is
Easier to, I think it's easier to do that the problem is what they do.
yes, we have, yeah, that's another one. So let us write down what we already have. So we will make now a reduction tree from tree set. We will we understand that independent set problem is NP-complete and integer programming. We also know that clique problem is NP-complete. And now we will prove that vertex cover is NP-complete. So given a graph and a number k, can you find at most k nodes so that every edge has an endpoint among these k nodes? So every edge touches a selected node. Need some space. Okay, I guess I can remove this. So let me write down vertex cover problem. And there is a very easy relation between independent sets and vertex covers in a graph. So what could be this relation? So if I give it a vertex cover, I can see an independent set very easily in the graph.
Yes, the rest of it. The rest of the.
Yeah, exactly. So let me write this. So vertex cover problem. So the input is graph and game question exists a set of key nodes, most key nodes, or let's say exactly key nodes. It doesn't matter much. And such that every edge has endpoint among let us do an example. So this one has a vertex cover of size 3. Because we can select this one and this one. Now one edge is not covered yet. This one is not covered yet. So we need to select one of these two. For example, this. So vertex cover has set of size 3. Now let us look to the nodes that are not in the vertex cover. So there are 2 of them and they are not connected. And this is very logical. If 2 nodes are not in, because imagine they were connected, then these other nodes are not the vertex cover. So minimal size of an independent set is maximal size of a vertex cover, number of nodes minus. So if we have a vertex cover of size 3, we have independent set of size 2. If there is no vertex cover of size 2, then there is no independent set of size 3. And so reduction is very clear. It's a really easy reduction. So and set reduces the vertex cover, and so G of K goes to G number of nodes minus K. That's reduction. And now reduction also goes vice versa, but we don't. And so now we have proven that independent set reduces to vertex cover. So let's do one more problem and then we quit the lecture. So there is the dominating set problem. I think it was in the homework, if I remember correctly, but I changed the name so that it's a bit harder for ChatGPT to solve it. So dominating set. So input graph and number K. And the question is, can you find K nodes so that every node is either among these K nodes or adjacent to one of them?
Yeah.
Exist.
Those misspelled make it even farther.
Yeah.
Oh, yeah.
I used S instead of C or something.
Yeah.
Oh, sorry.
Instead of P.
Yeah. Okay. Thank you. Exist of nodes such that neighborhood of G minus S the neighborhood of S is all the nodes minus S. So V is set of nodes.
The, no, the, which contains.
Yeah, it's even yeah, also sorry. V minus S, because neighborhood of S can contain elements from S. Yes, you're right. Okay, let me write it better. So N of S, you know this notation. So if S is a set of nodes, these are all the nodes that are connected to S. So in other words, every node not in this set S must have a neighbor inside S. So let's look for our example here. So do we have a dominating set of size 1? Can we choose one node so that every node neighbors it?
No.
So which node? No. Maybe 2? Can we have 2?
Yeah.
Yes.
This one and
Yeah, this one and this one. And so every node has that's not in the select, that has a neighbor selected. Okay. And so now we want to prove that dominating set is NP hard, so we will do it by reduction from vertex cover. Okay, this is a little bit dangerous because I forgot the reduction completely. So while coming here, I tried to remember it. And so the plan is to insert in every edge 2 nodes. And the number, and so here we have a graph and K, and so the K with in each edge. Okay, I will call it G prime. And the value of K is number of nodes plus number of edges. Plus K. No. Sorry, not number of nodes, K plus number of edges. So that's the value. Okay, so let me illustrate this. This will be mapped to space. Okay, I will write it here a bit smaller. So in every edge, I will insert 2 nodes. So this reduction is done in polynomial time, clearly, because yeah, that's really part. And so now I claim that if dominating set exists here, we have dominating set here, and the number of if we have vertex covered here, then we need a bit more for vertex cover. So if there is a vertex cover here, we have a dominating set here. And then, so first, the original nodes that we select are the same ones of the vertex cover. Like this. Okay. And now is the question for the other nodes. We choose each time the nodes that is away from the already selected nodes. And so here we need a dominating set, and the claim is choose these ones that are away from the dominating set. And if the both endpoints are already selected, it doesn't matter what we pick. And so the claim is that this is a dominating set of a size at most K plus number of edges. And so by construction, we chose the K nodes that are in the vertex cover, and we added 1 for each edge. That's clear. And it's a dominating set because each neighbor in the edge is selected. But also every unselected node here is also selected because okay, it works if there are no no isolated nodes. But for isolated nodes, it's clear we need to select them, of course. So I forgot to say in the reduction, there is a borderline case. If there is isolated node, then it's in both cases. Okay. So it's here. So you need plus number of isolated nodes. Because in the dominating set, we need to select it. Okay, sorry, and okay, so but okay, do I need to repeat? It's clear, right? And so select all the isolated nodes and then do this construction. So this direction, if vertex cover of size k exists, we have dominating set of this size. Now vice versa, if we have dominating set of this size, then we have vertex cover. And so first we forget about, okay, so note that here we are using certain structure. In the dominating set, we can enforce this structure. What is the main structure here? The main structure is that on each edge, there are two internal nodes and at most one of them is selected. If both nodes are selected, then I say, let's push one of the nodes to the side so that we have exactly one node selected in each edge. And so if both nodes, if we have something like this, and maybe this not, then let's move this one away. It doesn't matter which one we move away. And so we make sure that every edge has precisely one selected node. Okay. So, and now the selected nodes will form the vertex cover. And it's clear why it happens. So we drop isolated nodes. And so what will be the size of the vertex cover? So the size of dominating set minus the number of edges minus the isolated nodes. And so we have equivalence in both directions. So now we have proven from vertex cover that also dominating set is NP-complete. Okay. So this is the end of the lecture. No, when I'm supposed to stop? Oh, 5 minutes ago.
That all those problems are to be hard, but we never discussed why they are in NP.
Oh, sorry, yeah.
It's
Why they're in NP? Yeah, it's very important. So if we want, the task is to say a certain result is NP complete, then you have two tasks. You need to prove that it's an NP and prove that's NP hard. For NP hard, you need to present reduction and give the two conditions. So normally for the grade, so there in total there are 4 tasks. Present reduction, say that's polynomial time, and prove that it's equivalent. But first task is 1/4 of the mark. So just saying it's an NP because whatever dominating set, vertex cover is certificate or a non-deterministic machine does blah, blah, blah. It's already 1/4 of the mark. You have it anyway, if you just say it. And please say it because some clever students think it's too easy. But then I'm in trouble because it's against the grading rules. But okay, I will make exception. Yes, please comment. The lecture is finished. Okay, so then it will be 10-minute break. And yeah, I talked a bit too long. So let's start at 9:45. Okay. So, oh, and I forgot to print the seminar. You have it? Ah,